Today we're going to be talking about reinforced concrete beam design, specifically the context of rebar termination points with respect to Project Submittal 3 in CE 474 at the Air Force Academy. So we'll pick the project up with a 50-foot long beam, 36-foot long main span, and 14-foot long overhang. Now we need to find our MU curve, which is really the moment effects due to the factored loads. And we have to understand and determine the loading conditions that would give us the worst case positive moment and the worst case negative moment. As it turns out, this top loading condition will give us the worst case positive moment, and the bottom loading condition will give us the worst case negative moment. So we need to draw our moment envelope. And if we draw our moment diagram, or our MU curve, for the M positive max condition, we'll get something like this. If we draw the MU curve for the worst case negative moment, we'll get something like this. Those two together will give us the moment envelope for the beam and will allow us to start designing rebar. Now we could design a phi-mn as such to resist the worst case positive moment, and a phi-mn as such to resist the worst case negative moment. And we could run that amount of rebar across the entire 50-foot length of the beam if we wanted to. But to save money, we want to determine where exactly we need the red phi-mn to resist positive moment and where exactly we need the cross section of the beam representing the blue phi-mn to resist the worst case negative moment. We know by looking at this moment envelope, which is really our MU curve, or MU of X curve, that we don't need all of the positive moment resisting steel along the 50-foot length, nor do we need all of the negative moment resisting steel across the entire 50-foot length. So we'll start looking at sections of the ACI code to determine where we can cut off these bars. We'll first look at section 12.10.3, which says reinforcement shall extend beyond the point at which it's no longer required, or the theoretical cutoff point, for a distance equal to d or 12 dB, whichever is greater. So that's how we determine the first possible cutoff points for our continuing steel, or the weaker cross section on both the positive side and negative side. Going back to our drawings, what that allows us to do is have phi-mn 1 and phi-mn 2 for the positive moment resisting steel, and phi-mn 1 and phi-mn 2 for negative moment resisting steel. So we'll call this 1 phi-mn 2. We'll call this one phi-mn 1 and phi-mn 2. So we're going to alternate between phi-mn 1 and 2 for the positive moment resisting steel and phi-mn 1 and phi-mn 2 on the negative side. We just have to know when we can jump from the weaker cross section to the positive cross section and back. What we do is find the two theoretical cut points, which is where phi-mn of the weaker cross section intersects MU of X curve for the positive steel. And likewise, we'll find the two theoretical cut points where the weaker cross section and the negative moment resisting steel intersects the MU of X curve there. And what that last section of the code tells us is we find those theoretical cut points and then extend outwards a distance of d or 12 dB, whichever is greater. So we'll find those 4 points and we'll extend outward towards the lower MU a distance of d or 12 dB. And those 4 new points become our 4 first possible termination points. Again, the dark 4 dots where phi mn, the weaker cross section, intersects mu of x are our theoretical cut points. And those 4 gray dots, a distance of d or 12 dB away, represent our first possible termination points. And those are the points where we can transition between our stronger cross section and our weaker cross section. If among those 4 first possible termination points we determine we're planning on terminating some rebar in a tension zone, we need to consider section 12.10.5. One of these 2 criteria need to be satisfied, either 12.10.5.1 or 12.10.5.3. To determine which one applies, we check, is phi mn continuing less than or greater than 2 mu? And we use the appropriate section depending on which is true. So we'll either be checking if phi vn is greater than or equal to 3/2 VU, or phi vn is greater than or equal to 4/3 VU. And this is really sections C and D on our project submittal. And just looking back at our picture of mu of x and our phi mn curves, we know that 12.10.5 applies because we have positive moment resisting steel on the bottom of a beam, and we have a positive moment. On the negative side, the blue curve, we have steel, negative moment resisting steel on the top of our beam, and we have a negative moment. So all 4 of these points, these gray points that I've drawn, do require us to check section 12.10.5. Now there are 2 ways to address section 12.10.5. If, say for example, we're using 12.10.5.1, if this is not true, if for example phi vn is less than 3/2 VU, we can do one of 2 things. Part C of PS-3 says if this is not true, we need to determine the stirrup spacing to make this true. So we can really squeeze in those stirrups to increase phi vn. Now in part D, that says we're locked into a certain stirrup spacing. We can't change that. So we can't change our phi vn side of this equation. So what part D asks us to do is extend that bar, so extend it past the first possible termination point that we solved for, which was the theoretical cut point plus D or 12 dB. Keep extending it past that point. Eventually we'll get to the point where the moment is small enough, the mu is small enough, where we may transition from 12.10.5.1 to 12.10.5.3. All along, when we extend that, we'll be changing our mu and our VU. Because remember, when dealing with section 12.10.5, the mu and the VU is not the mu max or VU max anywhere along the beam. It's the mu and VU at the first possible termination point. So once we've applied 12.10.5, we can either determine the stirrup spacing required for us to be able to terminate this bar in a tension zone, or we can extend the bar past the first possible termination point to a place where this equation holds true, either 12.10.5.1 or 12.10.5.3. 12.11.1 and 12.12.3 also come into play when designing a beam. We have to know where both the positive and negative steel must end. So where does the weaker cross section end? When we solve for the first possible termination point and applied 12.10.5, that was where the strong cross section ended and transitioned to the weak one. 12.11.1 and 12.12.3 are where the weak cross section end, and we don't need any steel at all. So 12.11.1 talks about positive moment reinforcement, and this wasn't asked for in our PS-3, but this says we need at least a third of the positive moment reinforcement in simple members and 1/4 the positive moment reinforcement in continuous members extending into the support. 12.12.3 did come into play in our assignment in section E, and this talked about the negative moment reinforcement. And negative moment reinforcement goes off of the inflection point, and it goes a distance not less than d 12 dB or ln over 16, whichever is greater. So going back to our curve here, we need to find the inflection point right here, or the m negative max intersects 0, our axis, and then back off a distance of either d 12 dB or ln over 16, and this is where our weaker cross-section or all negative moment reinforcing rebar can end. After that, part F asked us to compute development lengths using equation 12.1, and then later on it asked us to apply 12.11.3 to determine if the development length was less than or equal to 1.3 times mn over VU plus LA. So this is what part H asked us to do. Now remember, mn is the nominal moment strength, so it would be ASFY times the quantity d minus a over 2. VU is the shear strength given the particular loading case we're checking against. In part H, it happened to be the M positive max loading case, and we just need to make sure if this holds true. In reality, if this didn't hold true, what we could do is use smaller and greater numbers of rebar to decrease the development length. The final solution should look something like this, where we make sure our development length is short enough on the left side here, where the slope of our phi mn curve is steeper than the slope of our mu curve. At all points, we want to make sure our phi mn curve is greater than mu. And on the negative side, we want to make sure the absolute value of phi mn is always greater than mu. So notice this point here, this was our theoretical cut point, and we backed off a distance d or 12 dB. Same here, theoretical cut point, we backed off a distance d or 12 dB. Here was our inflection point, and we backed off a distance 12 dB, d or ln over 16. The final solution includes a elevation view with labels for all your bars and dimensions. So a final solution would not only be this elevation view on the bottom of the screen here, but would include dimensions of exactly where your rebar extends to and from, as shown above on the phi mn and mu of x curves. Finally, a bill of bars is something that would be helpful when you're ordering rebar from a supplier, and it's an overall summary of what size, how many bars of that size, and at what length you need. So hopefully this was a conceptual summary of PS-3. It would be important to understand all aspects of rebar cutoffs, how and where to transition from a strong cross-section to a weak cross-section, and where we no longer need any positive or negative reinforcement at all, such as the locations here and here. So this concludes the summary of PS3. Have a good day.